So, this is a class about chemical elements. Stuff is made up of chemical elements, and so you should know a bit about them to understand stuff. That's the green arrow. So the physical world is composed of key materials called elements. Elements are a basic chemical substance that cannot be divided into a simpler substance by any means. This is going to be one of those lectures where I basically read my slides to you so you don't get confused by my funny accent or anything like that. I want you to make sure you get all this down properly. And notice the green arrows, of course. So atoms are the basic building block of the universe and of stuff. So to understand stuff, you need to know atoms a bit. So an atom is the smallest portion of an element that exhibits all the chemical properties of that element. It's comprised of a central nucleus composed of protons, which are positively charged, and neutrons, which have no charge. Also electrons, which are negatively charged particles orbiting around the nucleus. These determine the chemical properties of the atom. So here on this table of the chemical elements we have all the elements. Here's one. This is carbon. And here you can see it has 6 protons and 6 neutrons in the middle, and a cloud of electrons going around the outside. So the number of protons is what determines the atomic number for that element, which is very important. And so that is the number you see on the table of the elements. So this is all like grade 11 chemistry or earlier, so I'm not expecting any great challenges here. Lead has a lot more protons, 82, and this is arranged in a number of shells which actually have letters, so you know which shell to go to at any given time. K, L, M, N, O, and P. Understanding this is very important for certain types of chemical analysis, which involve these electrons popping around from one shell to another. Now, as you may have noticed from the table of elements, there's a lot of elements, and some of them are more worth knowing than others. On here we have the atomic number of these elements, their name, their short name, their formula, which you should also be aware of, and this is actually their percentage of the Earth's crust. So here there's a number of very important ones. Oxygen. Oxygen is 46% of the Earth's crust, which is quite a lot. And you will see when we see more chemical formulae for minerals that oxygen tends to be in just about everything. Silicon, 27%, is also very important. A lot of the minerals on the Earth's surface are silicates, and so they will have a lot of silicon in them. Aluminium, less important, but still quite important. There's a lot of aluminosilicates in the world. Iron is very important. It's what most of the area below the crust is made of, so when that comes up to the surface, iron is involved. Calcium is very important, 5%. And there are other minerals as well. Major rock-forming ones, sodium, magnesium, and others. The only thing to really be aware of is when they do crazy things like give them their short letter names after the Latin name for the element, like ferrum. Very annoying. So that's all you really need to know about atoms. So that takes us on to what is a mineral. So knowing what a mineral is very important to understand many types of stuff. Apart from things made of minerals, of which there are many, there are things made of rocks, and rocks are made of minerals, and also things like pottery. Pottery is very important to archaeologists. Lithics are made of stone, so they're made of minerals, and also metals are actually minerals. They are crystals of iron and iron carbon crystals. So many things are actually minerals, and you should know something about them to understand stuff. So a mineral is a single crystalline phase in inorganic nature. That's just the sort of thing I would like to ask on a test. A single crystalline phase in inorganic nature. What is a mineral? And you will say a single crystalline phase in inorganic nature. So what does that mean? Well, a single phase may not be broken down mechanically into its components. For example, this is salt, the mineral halite. If you put that into a salt grinder, you get more salt, littler bits of salt. So you can't do anything to salt or any mineral mechanically that will break it down into anything other than other little bits of itself. So that's a single phase. A crystalline phase, there are many types of states in the world. There's a gaseous state. Here's a gas, molecules moving around quite freely. It's not a liquid state, things moving around a bit less freely. And it's not a solid state like this, which is everything's held fixed in a fixed pattern, but it's not quite the same as a crystalline state. In a crystalline state, all the atoms are bound into a rigid network extending in 3 dimensions. So this creates the well-known crystal structure found in crystalline objects, and in some cases gives them their external expression, the shape of, say, a quartz crystal you might want to dangle for some reason. So inorganic. So minerals form in inorganic environments and usually inorganic origins. So not organic. Nature. There are some synthetic materials which are similar to have all these other attributes, but they behave differently. So a single crystalline phase in inorganic nature. That's what a mineral is. So how you get these minerals is through bonding of elements. So there are various forms of attraction that exist between the atoms to form the crystal structure. The most important in mineralogy is called ionic bonding. Ionic bonding. And in this, the mineral contains alternating cations and anions. Cations have lost electrons and so are positively charged. Anions have gained electrons and are negatively charged. Electrostatic attraction keeps the atoms together. Here is an example. Sodium chloride. So here you can see this is a chloride. There could be many chlorides. Its formula is NaCl, sodium chloride. It makes the mineral halite. This is a hypothetical slice through a sodium chloride mineral. Here is the negative chlorine and the positive sodium. The cation is the sodium and the anion is the chlorine. So I'm now going to show you something that, if you pay close attention, will help you work out the entire rest of this lecture. The cat is on the left, the onion is on the right. Let me do that again. Okay. So just stare at the screen. Look at it and see. The cat. Just burn that into your mind. The cat is on the left, the onion is on the right. Cation on the left, anion on the right. Got it? Just burn that into your mind. Okay. So here's another example. This is lead sulfide. So this is a sulfide, also called PBS. Not that PBS, the mineral called galena, in which the cation is lead, Pb, and the anion is sulfur, making a sulfide. So sometimes the anion may be an anionic group kept together by covalency. A very good example of this is calcite, which is a carbonate, and gypsum, which is a sulfate. So in this case, here the anion, so the anion's on the right and the cation's on the left. So the cation is calcium and the anion is not one element but two, carbon and oxygen, making a carbonate. And here it's sulfur and oxygen, making a sulfate. So these are both anionic groups which form these minerals. Very pretty minerals they are too. Sometimes the cation may form a solid solution series, like the very important pyroxene group. So here's an example of a pyroxene diopside, a very nice green mineral you will find in metamorphic rocks. Here you can see it's a silicate, SiO2, and on the other side, the cation side, it has calcium and magnesium. Over here, however, there are related minerals which are calcium and iron, and so this forms a solid solution, and the closer it is to one corner, it will have more or less of different minerals, different elements. A very important mineral that you may be aware of is, of course, jadeite, which is a pyroxene, sodium aluminium silicate. So this brings us to this form of classification of minerals named after someone called Dana. No, not that one. This one, James Dwight Dana, who came up with mineral classification in 1858. And in this common method of classification for geologists and mineralogists, minerals are grouped together by anions and anionic groups. You have native elements, you have sulfides, oxides, halides, carbonates, sulfates and chromates, phosphates and arsenites and silicates, and don't worry about it. Now it's next lecture's problem, okay? So this, however, is what all that about anions and cations are leading into, the entire basis of the next lecture. However, we will talk a bit more about how you identify minerals. This is very important when you're identifying minerals. One of them is sight, what it looks like, and it may have specific shape, a specific color, a luster, which I'll say more about in a minute, cleavage, parting, and fracture. Also diaphaneity. And there are tests that you can do, simple tests, like hardness. How hard is it? The streak, magnetism, and sectility. Also acid reaction. So we'll go through a couple of those now, which you will know to be important by the presence of the green arrow. Luster is a term rather like it's shiny or dull, only more pretentious. And so metallic, a lot of metallic minerals, vitreous, and this is quartz, pearly, earthy, silky, adamantine. Cleavage. Cleavage is very important, and you can see this is governed by the crystalline atomic structure of the mineral. This is got these cracks, are not cracks, they're sort of partings along the atomic structure of the mineral itself, and they will always be completely uniform. So hence they're very diagnostic. So you'll have a perfect cleavage, which creates perfectly flat surfaces like this one does. You will have a poor cleavage, in which the surfaces are not perfectly flat but consistent and parallel. And then we'll have a parting, which appears to be just a simple fracture, but they're always parallel, so it might break along this way and sort of along this way, more or less in the same direction. Fracture is in fact just, it breaks. For fracture, there are two quite important types of fracture. There is conchoidal fracture, and there is everything else, uneven, hackly, etc., etc. Conchoidal is very important because it's diagnostic of isotropic materials. This is one isotropic material. This is quartz. Its atomic structure, and it has a rigid crystalline structure, is uniform in every direction. You know, which way you hit it, it will break in a uniform way. It won't break in strange ways through cleavages or anything like that. This one is obsidian, and this is a volcanic glass, and this will also break in very predictable ways. They're called conchoidal after a shell. And so these shell-shaped breaks are very, very diagnostic. Diaphaneity is quite important. It's basically talking about how transparent the mineral is. And you can have transparent minerals. You can have translucent minerals in which light passes, just not very clearly. And then opaque minerals, which you can't see through at all. Now, of very great importance is hardness. And for this, we have the Mohs scale of hardness. So that would be not Larry, not Curly, but Mohs scale of hardness. Although actually it's this Mohs, Friedrich Mohs, who in 1832 proposed his scale of hardness. And it looks like this, and it's very important, as you can tell, by all the green arrows here. Now this sort of thing is just the sort of thing I could put lots of questions like, what has a hardness of 4? And you would say fluorite. So it's a good thing to memorize and to know how you can use hardness to... Yeah, you really should turn your phone off before a lecture, even a recorded lecture. So I might ask you, what's a mineral which is softer than a fingernail? And you would say, well, it must be gypsum or talc. Or it's harder than a fingernail, but softer than a copper coin, calcite. And so there's all sorts of very important rocks and minerals that are of these hardnesses. And so this is a way you can distinguish between them. There is streak, which is probably not particularly useful to you. That's why there's no green arrow, which is a strange thing whereby minerals which are like dark, like this, and you rub it against a tile, and it creates a streak, which is a completely different color. Like this black mineral creates a red streak, and this yellow mineral makes a black streak. And magnetism, of course, is very important if you are a mineral like magnetite, which is very magnetic. And so again, that's another very simple one. What's a magnetic mineral? And if you don't get magnetite, that's really not very good. Acid reaction is from the application of dilute hydrochloric acid, and you put this on a softish white mineral, and if it effervesces like that, it's calcite, which is very useful. So that is your introduction to minerals and the atoms that make them up. And in the next lecture, we will be looking at minerals in more detail. Thank you.